Okay, so I am looking at page 128 in your notes, and I want to do sample problem number 3. This represents the third type of calorimetry problem where we're doing a chemical reaction inside that coffee cup. Now the type of chemical reaction that I'm looking at, I'm mixing 20 milliliters of aqueous potassium hydroxide. I've got potassium hydroxide, and I'm mixing it together with 60 milliliters of aqueous hydrochloric acid. The type of reaction that I'm looking at here is a neutralization reaction. And I know that because I'm mixing together base plus acid. The other thing I want to notice about this reaction here is my temperatures. Both the acid and the base are starting at this initial temperature of 25 degrees Celsius. This is my initial temperature. And the final temperature inside that coffee cup is 60 degrees Celsius. Here's my T final is that 60 degrees Celsius. Now I can tell, because I'm going to look at delta T is equal to T final minus T initial. That delta T for this chemical reaction is going to be 60.0 degrees Celsius minus 25 degrees. My delta T inside this coffee cup is going to be that difference there. It's going to be 35.0 degrees Celsius. Now looking at this delta T, because it is a positive number, I want to think about what type of reaction is happening inside my coffee cup. Delta T is positive, in which case the reaction must be releasing heat to heat up the solution inside. So what I can say about this reaction, because delta T is positive, it must be exothermic. And I can tell that by looking at the change in temperature that's given to me in the problem. Now the thing that I'm trying to find for this reaction is I want to find how much heat is released. So the question here says find out how much heat is released, the amount of heat released by this neutralization reaction. This is the thing that I'm trying to find, and the term that I'm really solving for in my equations is Q reaction. That's the heat that's being released by the chemical reaction. That's what I want to solve for. Now the place that I start these calorimetry problems is always the same. I'm always going to start with this general format of Q lost is equal to negative Q gained. Now whatever's losing heat inside my coffee cup has to be giving it to whatever's gaining heat inside my coffee cup because it's an isolated system, so all the heat change is happening inside that coffee cup. The negative sign here, my Q lost equals negative Q gained, is just to help me keep track of my signs. Okay, so let me start to plug into this Q lost is equal to negative Q gained. This Q reaction term is something that I'm going to be plugging into my equation. Now because the reaction is exothermic, I'm trying to think, where does this Q reaction term go? An exothermic reaction is one that loses heat. It releases it into the surroundings, in this case the aqueous solution that my reaction is happening in. I'm going to set Q reaction as Q loss because my reaction is exothermic. So when I break down my Q loss is equal to negative Q gained, my next step is I'm going to take Q reaction and I'm putting it in place of Q loss because the reaction is exothermic. Now I want to think to myself, okay, I'm on the opposite side. I want to know what's gaining heat in this chemical reaction. The things that are gaining heat here, I'm going to maintain my negative sign, is that the Q of the aqueous solution is going up. That temperature is going from 25 degrees Celsius to 60 degrees Celsius. When I mix my acid and base together, it's gaining heat. The other thing that could be gaining heat is the Q of my calorimeter. Now sometimes we keep this term and sometimes we ignore it. The calorimeter, what I mean by that when I say Q of the calorimeter, is that I mean the coffee cup. The coffee cup itself can be gaining heat and taking it away from the solution. Sometimes we ignore that term and sometimes we don't. Now, because this problem here says that the heat gained by the calorimeter is negligible, what that means is that I'm going to set Q calorimeter equal to 0. I'm going to assume that it doesn't gain any heat, and I'm just going to ignore that term. In which case, what my equation becomes is Q reaction is equal to the negative Q of my aqueous solution. That's all that I've got left. The thing that I'm trying to find is I'm trying to find this Q reaction. This is the term, this is the thing that I want to find. I want to get a value in joules or kilojoules of my Q reaction. I have to break down the right-hand side of the equation into something that I can plug into. So that's what I'm doing next. I'm solving for Q reaction here. I'm going to maintain this left side of my equation. In place of the Q of the aqueous solution, I'm going to keep that negative sign. I need the mass of my aqueous solution times the specific heat capacity times the change in temperature. Now remember that this Q equals mc delta T is an equation that's on your green sheet. And this is what we're going to be plugging into. Now I already figured out delta T. The aqueous solution is increasing temperature to 35.0 degrees Celsius. In terms of mass, let me work on that next here. So for the mass of my aqueous solution, I'm going back to the problem here. And what I see, what I'm given about my aqueous solution is I've got 20.0 milliliters of base, and I'm adding it together with 60.0 milliliters of acid. So this gives me a total volume of my aqueous solution of 80.0 milliliters. Now, based on this part here in the problem that I'm going to assume that the density is for every 1 milliliter of solution, it has a mass of 1 gram. I'm going to assume that density is 1 gram per milliliter. That means that the mass of my aqueous solution is 80.0 grams. So this is what I'm plugging into M in my equation. Next up, that C, my cursive C, is a constant, and it's on your green sheet. This C for water, I'm going to assume that the C of my aqueous solution is the same as the specific heat capacity of just pure water. And I'm going to use that value, 4.186 joules per gram degrees Celsius. Now remember, I'm solving for this Q reaction and I'm plugging into the right-hand side of the equation. So let me get my equation set up here. So Q reaction, the thing that I'm solving for, is going to be negative. My mass here is that 80.0 grams. My specific heat capacity of the aqueous solution is the same as that of water, so I'm using my constant, 4.186 joules, grams, degrees Celsius. Those are my units. And I'm going to multiply that by the delta T of my aqueous solution, so I'm going to multiply that by 35.0 degrees Celsius. That's the delta T that I calculated originally. I'm going to do my math, so I'm going to do 80.0 times 4.186 times 35.0 degrees Celsius. Notice how my units are canceling, so I've got grams here is going to cancel with grams in the denominator. Degrees Celsius will cancel with degrees Celsius, and I've got these units of joules left over. I'm solving for Q reaction. This is the thing that I want as my answer. And I'm going to have these units of joules. I got a really big number with a negative sign here, so I got negative 11,000 700, and my units here are joules. I rounded to 3 significant figures because that's what I had for delta T, and that's what I had for my mass. I could also report my number here in kilojoules. This would be the same as negative 11.7 kilojoules. And either one of those answers is fine. Joules or kilojoules is totally fine. This is how much heat is being released by the neutralization reaction. This is what we calculated, and this is what I'm doing in my calorimetry problem here. It makes sense that I have a negative sign here because remember we said that this is an exothermic reaction. The temperature went up, the reaction must be releasing heat, and to communicate that it's an exothermic reaction, we gotta have that negative sign in our problem here. So this is the answer. This is Q reaction, how much heat is being released when I mix 20 mils of base with that 60 mils of hydrochloric acid.